Okay, so thanks for the invitation. I'm happy to tell you a bit about physical unclonable functions, and especially about memory-based PUFs that we're going to look at, or that we are investigating at the moment. So let's start. Why are we using PUFs, or what are PUFs? So the main motivation comes from the question whether physical objects do have unique fingerprints. Like every human has a fingerprint, and we ask ourselves, I mean, do also physical objects like chips or also other things like cables do have unique fingerprints. Yeah? And if yes, can we find them? Can we measure them, and can we use them for something of importance? And a related question: if we can measure these characteristics securely, I mean, can we use these characteristics to build trust in a complicated system? So can we use PUFs as some kind of trust anchor on which we rely the security of or base the security of larger systems? And actually this is possible, and I'm going to briefly show you how this works in the coming 20-25 minutes. So one of the main motivation is that we have now an increasing number of low-end devices that get connected. Think of mobile devices, car-to-X communication, Internet of Things, sensor nodes, etc. And often those devices have no dedicated security features. So if you want to have some kind of hardware root of trust, you typically have to look at features that are already there in those devices and try to utilize them. And fortunately, some of those devices indeed have PUFs, right? As I'm going to show you in a minute. And they can potentially be used to secure a larger system. So what's a PUF? It's basically some kind of function that is embedded into a physical object, and you can query this function, and the function gives you a response. Yeah? Why is it only a function under quotes? Yeah, because this response that the PUF generates is not exact. So it's not, you do not always get the same response, but you get a response that's close enough. Yeah? That is up to noise, identical to the response that you expect. And a stable response actually depends on the challenge, so how you measure the response, and it also depends on the specific physical properties of the object. Yeah, and typically during the production process, each and every instance of your PUF will be slightly different. Yeah? And these differences are what we basically use. Yeah? So there are many different PUFs. So historically, optical devices were the first PUFs, where you basically take some transparent material, mix it randomly with particles, reflective particles, then you shine a laser beam onto it, and what you get is a speckle pattern as response. You can digitalize this speckle pattern, and you can try to error correct. Now, these were historically the first PUFs, but they had, of course, the main drawback that you need optical measurement equipment, which is hard to integrate in any kind of IoT device. So people looked at alternatives, whether you can actually build PUFs also from within silicon. And what people typically use there is the fact that if you build silicon, then the propagation delay of the individual elements is slightly different. Yeah? So you build a basic logic gates, and those logic gates, they require a certain amount of time to actually compute the function. Yeah? And this time is somehow unique. So they are slower devices and they are faster devices. And even though those devices may look identical from a design point of view, the manufacturing process makes them unique. So there will be slight deviations in timing. And those timing characteristics you can use as PUFs. Yeah, there were arbiter PUFs, for example. There were ring oscillator PUFs that utilize these minor differences in the delay of electronic signals. The class of PUFs that I work on basically are memory-based PUFs. So PUFs that are based on memory cells. And if you remember how an SRAM memory cell looks like, an SRAM cell consists of two cross-coupled inverters that you can see here on the right-hand side. And if you would power on such a device, and if those two inverters would be completely identical, you would get an infinite oscillation signal that races through those two inverters. But unfortunately, or fortunately for us, those inverters are slightly different. One is a little bit bigger than the other one. That means after a finite time, this race through these circuits will be over, and one of the two inverters will dominate, and this one will drive the signal towards a predefined value. Yeah. So in theory, you get an infinite loop on startup. In practice, you do not see this. In practice, there will be a certain bit in your memory cell, and which bit you get, so whether it's a 0 or a 1, this will largely depend on the physical characteristics, so which of those two inverters is slightly bigger. And the nice thing is that it's stable. So if you power on an SRAM cell repeatedly, then you will typically get always the same result in that cell. It will be either 0 or 1. It's random, but it's stable. That is, it's a PUF. Right? So the SRAM PUF basically consists of the following idea. You take an uninitialized SRAM cell, you power it on, and you read out the value. And this value will be highly unique to a specific device. How can you measure this uniqueness? Well, there are a couple of properties that you can measure and use to determine the quality of the PUF. For example, the Hamming weight. So you look at the number of bits that come up with 0 or 1. Ideally, the relative Hamming weights should be 0.5. You can compute what's called the intra-Hamming distance. So you can repeatedly power on your SRAM cell and see how often does a cell in one run come up with a 0 and in one run come up with a 1. And relatively over all cells, those differences should be 0. Yeah? And if you get an intra-Hamming distance of 0, you get stability. On the other hand, you can a PUF should be highly unique to a device. So that means if you take two different devices, read out the PUF of two different devices, they should be independent. Yeah? That means the Hamming distance between those two measurements should be relatively close to 0.5. And if you do this, you will get results like this. So on the right-hand side, you can see the power up startup pattern of an SRAM bank. A blank pixel means a 0, a white pixel means a 1. And on the left-hand side, you can, for example, see the intra-Hamming distance, which is in all cases close to 0 over all runs. And here you can see, for example, the inter-Hamming distance, which is close to the value of 0.5. Of course, there's noise in there, but these SRAM PUFs tend to be rather good. So they tend to be unique for each device, and they tend to give you a lot of randomness. Yeah, then you can, of course, ask your question, I mean, what happens with other memory types like DRAMs? DRAMs work in a very, very different way. So a DRAM cell consists of a capacitor and a transistor, and the bit is stored as a charge in this capacitor. Yeah? But the problem is that this charge leaks over time. That means the memory controller needs to refresh this charge once in a while, and it does this automatically for you. But if you do not refresh this, then it turns out that this leakage that is stored in this capacitor will disappear after a certain point in time. There are like potential leakage paths where this charge can disappear into neighboring cells, into wires, etc. But that means that after a certain period of time without the refresh, your charge will be gone. And again, the time it takes until the charge is gone, again, is unique for a single DRAM cell. Yeah? That means you can generate a DRAM PUF by doing the following thing. You start with DRAM that's ready for ordinary use. You try to disable DRAM refresh into a memory controller, yeah, for a certain period or for a certain fragment of your DRAM, which is called the logical PUF. Then you simply wait for a certain period of time. And while you wait, some of those cells will have lost charge. That means the bits that were stored there disappeared. Yeah? And then after a certain period of time, you enable refresh again, so you stop the decay and you read out the DRAM to extract the PUF measurement. And basically the PUF measurement is the position of all the bits where the errors appeared due to the end of the refresh procedure. Yeah? And it turns out that this the position where those errors occur are highly characteristic. Yeah? So over time, more and more of those bits will flip, but always the same bits will flip if you do this experiment in a repeated manner. Again, you can compute intra and inter distances. Just to give you two of those slides of those plots, you can see that the robustness is rather good. So for the same PUF, the same challenge should always produce a similar response. This is this plot on the right-hand side. So you see the histogram is skewed to the right-hand side, whereas the PUF is unique. So if you take two different memory cells, let them decay and compare the PUF characteristics, well, the distance between them is rather low. So the other histogram is skewed towards zero. So again, you have a nice PUF characteristics. You can distinguish different devices, and you get a stable response. Yeah, then of course you can also ask the question, well, you have now measured this at room temperature under certain conditions. What happens if it gets cold outside? What happens if you take your device, use it in winter? Is it stable? And this is indeed a good question. So you have to test temperature stability and stability to other environmental conditions. And we did this. You can see our climate chamber here. And basically, yes, some of the PUFs really have this nice temperature stability. And of course, you can also ask whether certain other conditions influence a PUF. We also checked, for example, radiation, background radiation in a physics lab. And also there, we found that the PUFs are not that affected by background radiation. Just another remark, so DRAM and SRAM PUFs are not the only PUFs that you can generate out of memory cells. There are also other PUF types. For example, we proposed the Rowhammer PUF a couple of years ago, and it turns out that if you repeatedly write to DRAM cells, you can introduce errors in neighboring memory cells. This is well known, right? This was the basis of Rowhammer attacks, which were very prominent a couple of years ago. But what we found out that the location of the errors is quite unique. So if you always hammer the same row, you will, with a very high probability, always get the same bit flips that flip, right? Again, because which bits flip are based on the physical characteristics of the device. So again, the indices of the bits that flip have PUF characteristics. It's not so easy to really exploit this PUF, but again, you see PUF characteristics in a memory set. So these are basically tricks of the trade to generate PUF behavior in memory. So you can power on uninitialized memory, you can let memory decay, or you can repeatedly access it and try to introduce faults. And it turns out that all three strategies do work. Yeah, why do we do this? There are a couple of applications of PUFs where you can use the PUF measurements. The most classic application is, of course, device identification. So the PUF measurement is somewhat characteristic to a device. And if you see the same measurement again, after a certain period of time, well, you know that this is again the same device that I've seen before. So the protocol works like this. In an involvement phase, a server has access to the PUF. It queries the PUF with a challenge. It records a response. Then at a later point in time, it ships the PUF to a client, like it physically ships the PUF to a client, and this client can later on authenticate himself by using the PUF, because the server simply sends a challenge to the client. The client asks his PUF, gets a response, sends the response back, and the server simply verifies whether this response is identical to the response that he measured during the enrollment process. Yeah, and if you only use PUF challenge and response pairs only once, then this really gives you a secure authentication protocol. You can also use PUFs to store keys. So if you use crypto in an embedded device, you often have the problem that you have to store a cryptographic key on a device, which is rather difficult from a production point of view. PUFs are one very elegant solution because you can use a PUF to basically extract a key that is present in an object, but that was never embedded there. Yeah, this key basically emerges out of the physical production process of the device itself. Yeah? So the idea is you fix a PUF challenge, which is sold on a chip. Then whenever you need your key, you can query the PUF. Yeah? This PUF gives you a response that's potentially noisy, and then you have to have some kind of measurement or some kind of a correction mechanism that will correct any measurement errors, and that will give you finally a cryptographic key that's intrinsically stored in the device. There are actually products for this on the market. There are startups, there are small companies that market solutions based on memory PUFs to basically store cryptographic keys. But you can also do more things. You can also use PUFs as random number generator. So I mentioned before that PUF measurements tend to contain errors. And those slight errors you can use as nice true random numbers. Right? So you basically you query a PUF, and then if the PUF has enough noise, then you can simply use the PUF response as a pseudorandom number. What we also looked at is hardware-software binding. So you can also use a PUF to basically bind hardware with software, and that answers the problem whether you can protect IoT devices from firmware manipulations. So one trick there would be to say, well, I encrypt my firmware, put this encrypted firmware on my device, and then whenever I want to boot this firmware, I query the PUF for a decryption key, decrypt the firmware, and only then run it. Yeah? That has the advantage that the encrypted firmware will only work, so will only decrypt on one specific device and not on a cloned or a complete device. So you can even go a little bit further. That's what we've done last year, where we tried to use PUFs to protect the integrity of software. And there the idea was that we embed in our program, in our binary, what we call check functions and response functions. And the check functions, on the one hand, computed a device fingerprint through a PUF. So they repeatedly query the PUF to generate some kind of stable but random device identifier, which generated authentication values. And then we had some self-checksumming code in the binary that would validate the integrity of the running code. And then both authenticity and integrity values could be fed into response functions that would check whether, well, the device is still authentic on which the software is running, and the integrity of the program code is still there. Yes, if that was the case, then we execute the code normally. Otherwise, we initiate program misbehavior that the program will eventually crash. Yeah? So with this trick, you can both bind a certain piece of software to a hardware, and you can also guarantee the integrity of some code. Yeah, that brings me actually to the end of my short 20-minute presentation. So I hope I showed you that PUFs are versatile tools in computer security. So they rely on manufacturing variations of devices. So even though many devices are produced exactly in the same manner due to manufacturing variations, they never look identical. And we use those small differences to provide a stable but noisy fingerprint. And those PUF responses can be used in various cryptographic applications, ranging from authentication over key generation until software protection. Still a couple of open challenges. At the moment, we have two projects where we look at novel architectures. So we look at novel memory architectures like memoristic memories that store content even if there are no, even if there is no power supply attached. So we want to see whether we can find PUFs there too. And together with the TU Chemnitz, we also have a project that looks at nanostructures, so upcoming novel alternatives to silicon, and whether we can find some PUFs there. There are also a couple of other open questions, like can we really use PUFs as trust anchors, like as some kind of TPM alternative? There have been a couple of ideas in that direction, but they still rely on rather strong assumptions. So we would like to have a more practical solution there. And of course, the race between attackers and designers is still ongoing. So there are many papers around there that try to machine learn PUFs, especially arbiter PUFs, have this unwanted property that if you see some PUF responses, you can predict future responses. That's not so prominent with SRAM, but that's mainly prominent with delay-based PUFs. So there, the question of course, is how can we prevent this, and of course also how can we come up with new machine learning techniques that are better. And finally, one could also look at invasive attacks. So what happens if you really destroy a PUF? If you tamper with it, can you break some of the security properties? Yeah, so I still believe that PUFs is an interesting research topic that has several open questions.